This is the story of a Titan Airways A321, tail number Golf Papa Oscar, Whiskey November. On the 26th of February, a Titan Airways Airbus A321 was flying from London's Gatwick Airport to London's Stansted Airport. You might think that that's a short flight. You could drive that distance in about an hour. You see, this was a repositioning flight. There weren't any passengers on board. All this flight was meant to accomplish was to get the plane to Stansted. At 11:49 p.m. on the 26th of February, the A321 was pushed back from the stand. As the plane inched backwards, the pilots went through the process to start the engines. Engine number 2 roared to life, and the pilots then turned their attention to engine number 1. But the engine wouldn't start. On the ECAM, or the Electronic Centralized Aircraft Monitoring System, a fault appeared. Engine 1 ignition fault. No problem, they tried again. No luck this time. They had another fault on engine number 1. They got ready to try again. The captain was on the phone with technicians, and he said that if this engine did not light on the third try, then they would not be able to leave. On the third try, that dreaded engine 1 fail warning popped up for a few seconds, but it went away. Engine number 1 was good to go. The captain glanced at the instruments just to make sure that engine number 1 was working as intended. Once at the runway, the crew powered the engines up just a bit to see if they were okay. You can never be too cautious after all. With that out of the way, at 12:09 a.m., the plane started rolling down the runway. The plane lifted off into the dark night, and it climbed. As it passed through 500 feet, their climb was interrupted by loud bangs. It was coming from engine number 1. The engine was surging. The engine readings were all over the place, and the plane fishtailed from side to side. The captain fought to keep the plane under control. Even though the throttles were in the maximum continuous thrust detent, power delivered by engine number 1 started to fall. Soon, it was at 40%. A few airline employees in the cabin saw flames shooting out from the engine. They tried to get in touch with the crew. The captain put out a mayday call. He wanted to get to runway 26 left as fast as possible. He disengaged the autopilot and put the plane into a right-hand turn. As the crew did this, they pulled engine number 1 back to idle. Whatever was wrong, they did not want to make it worse. As they leveled the plane out at 3,600 feet, the control panel told them of another problem. Engine number 2 was starting to act up. The warning, engine 2 stall, flashed on the screen. Fearing the loss of engine number 2, the captain pushed engine number 1 to about 50%. They were down, but not out. The captain noticed that both engines were more stable at a low thrust setting. The engines gave them just enough power to stay airborne. The first officer was busy setting up a return to runway 26 left. The plane flew a circuit around the airport. Can you imagine how tense those pilots must have been? Their lives depended on 2 malfunctioning engines holding out for just long enough. Cautiously, they lined up with the runway. They were 9 nautical miles away. The captain was still concerned about a total engine failure, so he flew the approach a bit higher than usual. If the worst did come to pass, then they'd be able to glide a bit further than usual. But they were fine. The plane touched down safely at 12:20 a.m. The plane was fine on final approach, and they even used reverse thrust. They pulled onto a taxiway and shut the engines down. None of the 7 people on board were hurt in any way. With the plane intact and the pilots alive and well, the investigators knew exactly where to focus: the engines. Finding out why the engines behaved so erratically on the climb out would be the key to unlocking this mystery. So they took apart the engine and went through it bit by bit. They got to a part in the engine called the HMU, or the hydromechanical unit. It basically accepts electrical inputs from a computer and then controls fuel pressure. This fuel pressure then in turn controls a few actuators in the engine. In addition to this, the HMU has a valve in it called the FMV, or the fuel metering valve. This valve controls the pressure of the fuel sent into the combustion chamber. To test these further, they were packed up and sent for testing. When technicians inspected the HMU, they found that it took a significant amount of force to move parts of both HMUs. Tearing the HMUs down, they found a gelatinous substance inside. It was not supposed to be there. Tolerances inside the HMU were low. Any sort of debris, even a bit of gelatinous material, could seriously hinder the operation of the HMU. That would cause massive problems for the engine. So, what was this foreign debris inside the HMU? They tested it. It was made up of calcium and some other stuff. Looking back at the maintenance history of the plane, they immediately knew what it was. Earlier tests done on the plane showed that it had some microbial contamination in its fuel system. To fix this issue, they needed to add a biocide called kathon into the fuel of the plane. This would inhibit bacterial growth inside the fuel system of the airplane. Somehow, kathon had gotten into the HMU and jammed it, making it hard for them to regulate the engines. Looking over the procedure for this biocide treatment, they saw that to fix the bacterial issue, the kathon concentration in the fuel had to be 100 parts per million, or ppm. They decided to pay the base engineer that did the biocide treatment a visit to see how he went about adding the kathon. Talking to him, they found out that he had never done this before, but he felt that it was, quote, an easy job. But he did have some trouble. He did not know what the term ppm meant, and the term was not defined in the aircraft maintenance manuals. There was another engineer who had done this procedure before, but he was nowhere to be found. So, faced with something he did not know, he did what all of us do. He fired up his laptop and searched the web. An online calculator told him that he needed to add 60 kilos or 132 pounds of kathon to the fuel tanks to hit the needed 100 ppm concentration. In reality, adding that much kathon took the kathon concentration in the fuel to about 3,800 ppm, 38 times the required amount. When asked about the specifics, he couldn't recall what website he used. But not to worry, the investigators were in luck. When the maintenance engineers were told about what happened, another engineer came forward. He had done the exact same thing to another plane. Don't worry, the second plane was going into long-term storage. They asked the engineer who worked on the second plane about the procedure. He too was unaware of what the term ppm meant. Like the first engineer, he consulted the aircraft manuals, but it was no help. Again, like the first engineer, he too searched the internet. He found a calculator that converted ppm values into percentages. When he punched in 100 ppm into the calculator, it told him that the equivalent percentage was decimal zero 0.01. They were adding about 6,200 kilos or 13,000 pounds of fuel into the wing tanks. Decimal zero 0.01% of that is about 60 kilos or 130 pounds. The mistake here is that the calculations had to be done by volume, not by mass. But to the second engineer, this didn't feel right. He consulted with the other engineer who worked on the accident plane. He confirmed that this is how he too had done it. But the second engineer kept looking for a way to double-check his work. He didn't trust the internet per se. He tried the packaging of the kathon to see if that would be of any help. It was not. So now we know how the kathon got there. The engineers just didn't know how to do it. Here's a quote from the report. They did not have the background knowledge they needed to do the calculation correctly, given the sources of information that they had access to. End quote. To do this task correctly, they had to know what ppm meant. Then they had to convert the weights into volume by using the specific gravity of the fuel and the biocide. These important values were not given anywhere. Ironically, they had to look it up online. Nothing about what they did tipped them off about their mistake. They hadn't done this before, so they did not have any experience to fall back on, and the kathon came in 150 kilo or 300-pound bags. So 60 kilos doesn't seem like a wrong amount. But we're not done. There were two more mistakes. The aircraft manuals that they referred to expected the engineers to mix the fuel and the kathon together and to then pump it into the tanks, but it did not make that clear. How should the fuel and kathon be mixed together? It didn't tell. Also, they did not have the equipment needed to mix fuel and kathon outside the plane, so the engineers just dropped the kathon into the tanks without mixing it enough. So the kathon settled at the bottom of the tank. What else is at the bottom of the tank, you ask? Just the fuel pump inlets. So when the plane was taking off, fuel inlets were submerged by kathon-rich fuel, which sent this kathon-rich fuel straight to the HMU. Before we wrap this video up, there's one final question to answer. Maintenance was finished on this plane on the 24th of February, and this accident happened on the 26th of February. That's a lot of time for this problem to go undetected. But you see, people had detected this problem. After the biocidal treatment, the first flight that the plane undertook was from Larnaca to Stansted. This flight went off without a hitch. After that, the plane took another flight from Stansted to Gatwick. On this flight, they did have some issues. Fuel flow was all over the place. High pressure fuel valves had trouble opening, and a couple of ECAM error messages. After that, the plane had a flight from Gatwick to Krakow, and no issues were found for that flight. On the Krakow to Gatwick leg, the problems returned. The fuel flow was erratic, and high pressure fuel valves were having issues. After having these problems, the pilots recorded the problems in the technical logbook, and the plane was handed over to the technicians. To troubleshoot the issue, they turned to a portal called AirNav. It contained the information needed to troubleshoot all the planes in the Titan Airways fleet. The technician hit a button which allowed him to access all the procedures for all the planes in the Titan Airways fleet. Among the listed procedures were two procedures. The name of one of the procedures started with the letters CFMI, and the other one started with CFML, planes with CFM56 engines and planes with LEAP 1A engines. The technician did not know that. He thought that the airline only operated planes with CFM engines, and so he chose that procedure. In reality, this plane was equipped with LEAP engines. The technician had done the diagnostic test for the wrong type of engine. The CFM procedure called for an external inspection, while the LEAP procedure called for a borescope inspection of the engines and sides. Had this been done, they would have seen white deposits inside the engine, and the plane would have been pulled from service, and none of this would have happened. Now I want to hear what you guys think. What do you think about the engineers who miscalculated the amount of Cathon? They were asked to do something that they essentially had not been trained for. Sure, it's just a bit of multiplication, but without a background understanding of the subject, it's hard to get the right information to do the calculations. Do you think engineers should be doing procedures that they haven't been explicitly trained for? If you're a base engineer, I'd love to hear your thoughts. Thank you for watching this episode of Mini Air Crash Investigation. If you like the videos that I make, do consider liking and subscribing. It will really help the channel grow. I will catch you guys next time. Stay safe.